Hi, Assalamualaikum. Welcome to week 8 of our discussion on our subject of electrical drive train system. So we are still in topic 3 discussing about DC machines. This is basically the fourth and the last part of a discussion on DC machine where we are going to briefly look at the topics on drives and control of the DC machine that we have been studying for the last 3 weeks. So in this chapter, what we're going to look at is basically before I go into the details of what we have in the screen right now, we are going to discuss about two parts. The first one is the driver part. The driver means basically the what we call as power electronic circuitry that we need. So the components of electronic components that we need in order to drive or to supply power to our armature winding. Okay, and then second part we're going to do is we are going to be discussing about the control. So when we talk about control, it means in terms of basically how do we do in order to deliver the correct speed or the correct torque as we wish as wished by the application or the user of the machine. Okay, so in this first part we're going to talk about the driver or the motor drives. So the motor drives is basically we are not going to discuss about all the motor drives that is available in the industry. We're going to discuss about only two, which are the most common and basically the traditionally applied type of motor driver for DC machines. The first one being thyristor's drive, thyristors or triac drives driver. Okay, so this thyristor's drive was traditionally used, conventionally used for a larger type of motor, where especially when the machine is supplied with a three-phase supply, right? So we understand that when we have a three-phase supply, the supply is basically in AC. So there is the need of two function actually. So the first function is of course to rectify. So to rectify the AC current into DC current, and then secondly is not just to be able to control the machine. The driver need not just the correct form, which is DC, but also it need to be able to regulate or to change to vary the level of that DC current, because we know that the speed of the motor is proportional to the back EMF, therefore the voltage supplied to the machine. So there are two functions that need to be accomplished by the power electronic circuit. In this case, the driver is using a thyristor, which is the first one is to convert the AC from the power supply to DC, and secondly to once it is converted, to regulate, to adjust the level of that DC. So these two functions can be basically accomplished using what we call as thyristor. So thyristor is we are not in analog electronic subject or discussing about the semiconductors component, but in simple words, what a thyristor does is basically it functions just like a diode, where it can allow a current that goes through it if it is a forward bias. But the main difference with between a thyristor and diode is that, so in this figure over here, basically we are drawing it as a diode, noted as D1 from D1 to D6. The difference between a thyristor, so this is the symbol of thyristor, right? So the difference between thyristor and diode is that a thyristor, in order for it to allow the current pass, even if it is in forward bias, it need to be triggered. So there need to be a command at the what we call as the gate. So we can see that even in terms of symbol of a thyristor, it resembles the symbol of a diode, because it is basically a semiconductor like a diode that let current to go through it following a certain direction. But the only difference is that we have this terminal over here, which is basically the gate where we deliver the control. We will be able to tell the diode, the thyristor, when to operate, when to allow current to circulate. So the first part of rectification, converting from AC to DC, is just like a diode. So usually we use this form of configuration where we have 6 diode put in this configuration, where we will be able to at the end basically rectify in full wave. So in full wave means we will not just get only for example, if we look at the phase A, the red one, will not only get the positive part, but we also rectify or turn the negative part into positive part, so we get all the full wave rectification from the AC current. So at the end, we will have basically the output of the diode circuit, rectification circuit, rectifier. The output waveform is going to be like this. Okay, so that is if we employ a diode. But of course, employing a diode means we would only have this DC voltage. So we can see there is a pulsation of the output voltage. Therefore, we will have basically not the maximum VDC. At the end, the voltage that is viewed from the point of view of the motor. So all the circuitry is basically the thing that is symbolized in here, right? So we have the three phase that coming in, and in the output we have basically a single phase DC. So inside here is basically this circuit, and what we get in output is basically, so this is the input, what we get in output is this waveform. So this waveform is basically it is a pulsating waveform. There is the value at the end of the VDC will not be equals to the maximum voltage of this AC. It will be at a certain value which we could call as VDC average. Okay, so there is a calculation to find that. Okay, now as we can see now, VDC, if you're using diode, is going to be always constant like this. Therefore there will be only one V average. So therefore, as consequence, we know that the machine, imagine if our load over here is basically the winding of our DC machine here. So this DC machine will always rotate at the same constant speed, right? Because we are supplying with a constant voltage, therefore the speed is going to be a constant speed. So in order to change that, what we do is basically we use instead of a diode, imagine these are now not diode, they are thyristor. So they are something that looks like this. So in thyristor, what we can do is that we can adjust the moment when the thyristor operate or not operate. So at that time, basically, it can take into account, for example, if it operates at 90 degrees, it means that the first part of the wave form of the A signal will not be taken into account. It will take only into account the second part of the positive wave. So by doing so, the average voltage at the end, when we calculate it, it will be slightly lower than the full waveform if the diode start operating at 0 degree at the beginning. Okay, so this rectification and switching, so that's what we call as switching or firing. Firing means when does the thyristor works, take the input current. So the rectification plus the timing of this firing that is done by the thyristor circuit is the one is the thing that allow us to have a variable DC voltage, therefore variable DC speed. So that this is the most common motor driver using thyristor. And then this circuitry of thyristor, of course, as we mentioned just now, we need to decide if we want to control the level of voltage. We control it by changing the moment in which we fire the thyristor. So in order to be able to control the thyristor, basically we will have a control circuit. So here is basically we would have a certain microcontroller that will tell the thyristor, that will be connected to the gate of the thyristor, that will tell them to switch on or switch off depending on the control on the desire of the user. So that is determined by the speed reference. So if you look at this whole thing, so the driver is integrated inside a control schematic diagram. So in this part, I think you already understood. This is basically the field winding. It is basically a thyristor to control the field winding. So therefore, the magnetic field that is created on the stator, right? But in this control schematic diagram, what we can see is that in the motor we have a certain current control, current feedback, and then we also have a speed feedback. So from the information of the current and the speed, we will tell the thyristor, basically using the microcontroller, we will tell the thyristor whether we have achieved the reference speed or not. If it's not achieved, then it will continue to fire up, and it can fire up earlier or later, so that the voltage will go down or will be lower or higher depending on the speed reference. And then in current feedback, it is basically to control the current and the torque. Okay, so if you look here, the current feedback may be used to control the current surge or control the torque. So for example, when we start, there might be a current surge. Therefore, in this current feedback, we can basically program in our microcontroller to not switch on, to not fire the thyristor earlier, so that the current there will be no current surge, for example. And then we have an outer loop of what we call as speed feedback. So the speed feedback is basically the most important loop. We may not have the current loop. It is mostly for safety, to control the acceleration. But the most important thing is basically the speed feedback, or the speed loop, where we have basically a measurement of the real actual speed, and then we are comparing it using the microcontroller, comparing it with a reference speed, or the speed that is desired, that is defined by the user. Okay, so in general, what we are about control, we are going to talk about it later. Here we are going to talk only about the driver, which is the thyristor. So the thyristor allow two things when we use an AC supply. So it is basically especially for a larger DC machine. It allows us to rectify and adjust at the same time the level of DC voltage by adjusting the firing time. So here in more details, basically the operating principle of a thyristor. So what we have in this animation over here is basically on top is basically the output waveform. At the bottom, basically in blue over here, is basically the control signal for the gate. So we are taking an example, not this time a three-phase. Imagine if we only have one phase, because it is the same thing. It is applied just 3 times with a delay of 120 degree. But if we look at one single phase, what we are going to have is basically we are going to have this kind of configuration of thyristor. So what happened in blue is basically it's the moment at which we fire the thyristor. So the earlier, for example, here now, the earlier the thyristor is fired, then it will take into account all the waveform. Therefore, if we are taking into account all the waveform, we can see that the surface area underneath the curve is much higher. Therefore, the average voltage will be much higher as well. But if we delay the firing time, right? So for example, right now we delay the firing time, then we reduce the surface area underneath the AC curve. Therefore, if we calculate the voltage, average voltage, the voltage average will be reduced. And if we are completely at full basically, so here it is pi. If the firing angle is at pi, we will basically turn into a DC voltage of 0. So if we start at the beginning, we have full wave. If we start at the end, we will have 0. So the average voltage will be from maximum to minimum as the firing angle or firing time changes. Okay. So the angle alpha here is what we call as firing angle. And after the firing angle, what happens is basically the thyristor conduct the current. So therefore, we have in reality, if you use your oscilloscope to look at the waveform of the voltage in the output, you will basically observe this waveform. But of course, as the frequency is quite high at 50 hertz, from the point of view of the machine, of the winding of the machine, they may see basically something that is like an average voltage. We can average the voltage that is appearing on the output voltage over here. Okay, so of course, from the point of view of a mechanical inertia, when we have a look at the machine, we cannot really see the pulsation of the speed because due to the inertia of the shaft, right? So it continue to rotate pretty smoothly. But of course, if we look if we take a spectrum, we may see basically pulsation of speed and pulsation of torque. Okay, so in general, if I were to summarize the operating principle of a thyristor, we have the firing angle, the moment at which the gate of the thyristor is switched on or switched off. So it adjusts basically how much voltage is passed through the load. The thyristor will start to conduct current when it is on, and the thyristor will basically switch off automatically when the current goes below zero. So you need to switch it on back for the next cycle. So the control of this gate over here, noted as, for example, here IG1 and IG2, is basically connected to a microcontroller where you program the timing of the firing. Okay, and then we have, of course, the rectifier circuit. Thyristor is arranged in this way so that it will basically take both a positive part and a negative part. So for example, if the AC current now is in positive part, then the current will go through SCR1, it can go into SCR2, it goes into the load, and then it will goes back into the negative part through D2, go into the back into power supply. And if it is on negative part, then it goes to D1 and then SCR1, and then back into and then get into the load. Okay, so if I may repeat, so in positive part of the waveform over here, the current will go through this path, SCR1, go into the load, and then go into D2, go back into the power supply. But if you were in negative part of the waveform, then what's gonna happen is that the current will go through from the opposite direction. It will start from here, right? So this is the negative part. The current will go from here, get into SCR2, and then get into the load, and then get back to the power supply through the other terminal through D2. So in negative part, SCR1 and D1 that will operate, but in positive part of the AC waveform input, it is SCR1 and D2 that will operate. But in both cases, we can see that through the load, the current goes both in this direction. Therefore, that's why we have what we call as rectification, where all of the voltage that appears are all in positive side. Okay, so how do we calculate that average voltage in the output at the load? V average is equal to V max. V max is the peak voltage over here, divided by pi multiplied by 1 plus cosinus alpha. So what is alpha? Alpha, as we mentioned just now, is the firing angle. So this half sine wave is basically pi, or 180 degree. So alpha is basically a portion of that angle. We call it as firing angle. And the average current, of course, using Ohm law, average current is just voltage average divided by the load of the resistor. So in our case, RL will be the resistor of the winding of the armature. So that is the as we control alpha, we will rectify and at the same time change the average voltage, making it higher or lower, therefore controlling the speed of our machine to become faster or slower. So that is the first type of driver, where you are using thyristor as the power electronic components, and the most important thing is that we use thyristor because we need rectification, because the input supply is in AC. So now we are going to look at another type of driver, which is the chopper fed driver. Chopper, or in other term you might have heard about a PWM motor drive. So PWM motor drive, it is basically the difference with the thyristor driver just now is that for a machine, now we have a machine that is connected to a DC supply. So the supply is already in DC. So we have here that seems like something that symbolizes, for example, a battery. So it's a DC power supply. Like so this is especially true for application that is on board or embedded, where you are supplying it using a battery, such as a battery vehicle or any other embedded system. So a chopper converter is usually employed. Okay, So what is the difference? The difference is that instead of rectifying now, because we already have a DC supply, we don't need to rectify the voltage anymore. It is already in DC. So what we need to do now is just basically from a certain level of input DC supply, we need to adjust the level of that voltage, because again, the objective of a driver is basically to control the speed to make the motor go faster or slower, right? So in order to do that, we use a chopper circuit. So what is chopper? Chopper is basically an operation of switching on and switching off the power supply that is connected to our load. So for example, here the load is basically, so here we have the back EMF of the armature, we have the resistor and the inductor of our armature. So this is basically the load, right? So we are switching on and off the power supply that is connected to our DC machine armature. So what we can do is we switching on and off. The switching on and off is done by basically controlling a transistor type of component. So a transistor has a gate, so you controlling the current at the base. For example, if it is an IGBT, for example, by controlling the transistor, basically you open and close the circuit. And if you open and close the circuit pretty quickly with a pretty high frequency, what's going to happen is that you are going to make appears at the output voltage. So output voltage is of course the voltage across the load, something that looks like this. So yes, you may switch on and then switch off and then switch back on, switch off, switch back on, switch off and switch back on. What happens is that if the inertia of the machine is pretty high, we are going to see basically something that appears as average voltage, just like in chopper just now. The frequency is sufficiently high, the chopping is sufficiently high, therefore we can see basically a certain average voltage. So by varying the ratio of turning on and turning off, what we call as in this kind of driver, we call as duty cycle, the average output voltage can be varied from 0 to maximum supply voltage. So the duty cycle, the ratio of on off is basically usually in percentage. So 0%, when we say that the duty cycle is 0%, it means that we turn off all the way long. If the duty cycle is 80%, it means that we turn on for 80% of the period and we switch it off for 20% of the period. So you see there are two parameters in this chopper circuit. The first one is basically the duty cycle, or the ratio of turning on and turning off, the percentage. And then the next one is basically what we call as the chopping frequency. So there is a period over here in which you will turn on or turn off, that is determined by the chopping frequency. And then there is the ratio in which you will turn on and turn off, that's what we call as duty cycle. So this is also known as what we call as pulse width modulation, PWM. So this is a more used term to describe this kind of driver. So it's a PWM driver where you switch on and switch off using a transistor type of component to get an average voltage. So the component that we use to switching on and switching off is usually we use MOSFET or IGBT. So we have learned this in analog electronic in previous semesters. So the advantage of this component is especially that we don't waste any power. So if we are not using the power, we are basically if we're only using it, basically we are turning off the power supply. In comparison to the one that we have seen just now, the power supply are not turned off compared to this one. And then another thing that we need to remark as well, that is we need an adequately high chopping frequency. So the smoothness of the current, so as we switch on, then the current will rise. As switch off, the current will decrease. The smoothness of the output the current that goes through the armature of our DC machine will be depending also on the switching frequency. So how does it operate? So let's take a look at this figure over here. We have figure A, figure B. So figure A explain the operating mode when the transistor is on. So when the transistor is on, basically, so we have our power supply over here, so the current can start to circulate in this direction. So when it reach this node, it can only goes through the armature and not through the diode over here. So the diode over here is basically what we call as, so the diode is called as a free wheel diode or flyback diode. So we'll see later why is it called a free wheel, wheel as in wheel, WHEEL, free wheel diode or flyback diode. So in this case, for example, current cannot go through it because it is not in forward bias, it is in backward bias. So the current goes into the armature, so the armature receives the current, therefore the current in the armature will increase, right? And the current will get back to the power supply. So that is when when the control turns on the transistor, and then of course during it is turned on, the inductance of the armature will be somehow energized, right? So when we are turning off, so when we are now over here turning off the power supply by turning off the transistor, what's going to happen is that the power supply will be completely disconnected to the armature. There is a problem that we need to understand over here. Our inductors just now have been energized, and if we are disconnecting the circuit directly without any safety measure, what's going to happen is that we are going to observe a certain arc, right? So there is a peak of voltage that will suddenly be created, and we observe a certain arc, and that is not good for electronic component. So what we need to do is basically to consume the energy that has been stored in the inductance of the armature. So what we do is that we put what I mentioned just now as flyback or free wheel diode. Why we call it as free wheel? Because basically it allows that the energy that is stored in the inductor of our armature winding to recirculate back and to be consumed by the diode and the resistor of the armature winding itself. So the current that come out from the inductance that have been energized will circulate back in this part of circuit now to be consumed and to be gradually reduced. So what we can see is basically in this part the current gradually reduce until the circuit is turned on back again, so the cycle will repeat. So we have basically a sort of pulsation of current on the armature. Okay, so that's how it works. And as of course in this part the speed of the motor gonna drop a bit. In this part it's gonna increase a bit, but with high enough adequate frequency of chopping frequency of the PWM, we won't even notice it. We will only see something that is more or less average. So as we change the duty cycle, then we could increase or decrease the level of current. So that is a chopper fed driver or PWM motor driver. There is before we go into the control of the machine, of DC machine, there is a certain precision that I need to make. Of course, we have seen the thyristor driver and the chopper fed driver, but in reality, it is not just these two types separated. You may have a combination of both as well. So, for example, for now we have what we call as an inverter type driver. What happens is basically we in an inverter type driver, what we have is basically we have just like in thyristor, we have rectification. So it is for higher power machine, DC machine. We have a rectification first. Basically the rectification is done using the usual power diode, but not thyristor. But then later after rectification, we go once it is rectified, we add behind it a circuit of chopper or PWM driver. So we have a rectification using diode plus a chopper using PWM, using a transistor to make basically to rectify and then to adjust or basically change the level of the average output voltage. So it can be a combination of both. The thyristor is I would say less and less used. Is almost for older application because it consumes more energy. in the power electronic parts, in the driver part, using chopper is much better. So therefore, in inverter type of driver, usually we have rectifier using diode, power diode, and then PWM circuit part to adjust the level of the DC voltage. So now let's discuss about the controller. We are going to discuss about basically two types of control. It's not two types of controls. It is another one that we are going to look at after this. After this particular slide is basically an addition or an addition of a feature to the usual controller, to the visual control configuration. So what is the most common control configuration of a machine? The most common control configuration of machine is what we call as speed control. So we have a two-loop feedback control. So here we have the schematic diagram of the control. So here we have the machine, the armature of the machine, and this part is the part that we have seen just now. Is the power electronic or the driver part, where we have either thyristor or a chopper fed driver. And now we are going to discuss about all the other thing outside of it. So what we have here is what we call as two-loop feedback control. Is a speed feedback control. We have two loops. So what are the two loops? The first one is basically the one that is in the outer part. So when I talk about loop, it is the automatic control loop, like what you have learned in control system subject. So you have the outer part loop. So you can see here there is a certain command, which is a speed reference that's sent towards the system. And then at the end, you have a certain instrumentation to make a measurement, to measure the actual measurement. And then we have a comparator over here that is comparing the actual measurement and the reference that we are putting in. So reference is basically the desired speed, and then we are comparing with the actual or real speed. And then we put it into a speed controller. So the speed controller, what it does is basically it converts it into current, so that the current can be delivered into the machine. So in the first part of loop is the outer loop, what we call as a speed loop. The purpose is to control the speed, right? So we need feedback, as I mentioned, from an actual speed using here. In this example, it is a tacho generator. You may use an encoder or any other measurement that gives you speed. So the input speed is the speed reference. We are comparing it, and the controllers can translate it into current that is to be delivered to the machine. Okay, so if the speed of the tacho generator measured using the tacho generator is equal to the reference speed, then what happens is that the comparator will give an output of error of 0. So there is 0 error. 0 error means they should not send any current. So there will be no current that is be delivered to the inner loop. If there are no current delivered to inner loop, then the machine will stop to accelerate. So we'll try to maintain basically the speed that is asked by the speed reference. And then the second loop is the inner loop over here that are basically in gray box inside. So that is the loop of what we call as current loop. Okay, current loop. So the purpose of current loop is to control the current, therefore the torque. So in certain application, especially in a large machine, we have learned that if we ask the machine to go directly to an extreme maximum speed directly, what's going to happen is that there's going to be a peak of current due to the difference of the voltage supplied and the back EMF that we can measure on the motor. So there will be a surge of current. So the purpose of this loop is basically to control the current, therefore to control the torque as well. So it depends on purpose. There are in certain control, the purpose is just to control the current. It means that the purpose is electrical. They don't want the machine to pull too much current, therefore damaging a certain power electronic components. For example, your chopper, your transistor, or your thyristor, right? So in this current control, they might put a certain level of limitation, or it could be the implementation of controller of current is for mechanical purpose. For example, we don't want the machine to accelerate too much, because there might be a mechanical stress. So we're putting a certain limit of torque of current so that the machine won't accelerate too much. Okay, so again, to do that, of course, we need a certain measurement of the real current, of the actual current. So we would have a current probe or current sensor, and then the current will be compared to the reference current, and then the current controller will translate it into a command to the gate of the thyristor. For example, if you're using a thyristor motor driver. So if you look, for example, at this figure over here, it is basically the speed controller that is translating the speed error into current. So basically in it, we might have a lookup table or an equation that translates. So if I have a certain speed error, then it should be translated into a certain level of current. Therefore, the current will be the reference current that is sent into the current loop. Okay. So so we have two loops: speed loop and then current loop or torque loop, embedded one in another to control the speed of the machine and limit the current as well of the machine. Another loop may be added outside of the speed if we want to control the position. So that's the thing that we're going to look later, what we call as servo motor. Another precision that we have to make is that the power electronic component that actuates the delivery of power. So this is the driver part, the power electronic components. It can be, now here it is in the schematic diagram, it shows that inside it basically it is thyristor. So the controller of the current here is basically translating the current input into firing angle. If we remember just now, firing angle of the moment in which we will switch on or switch on the thyristor. But it can also be a duty cycle for a PWM driver, for example. Okay, so now the other addition to that, if we need more than just velocity or speed control, we might also want to do a position control. So that's what we call as DC servo drives. So DC servo drives is the term used when a motor can be position controlled. It means it's not just the speed that is being controlled, it's also the position. It is especially used in the applications such as robotic, where you want the motor to move from one spot to another spot. I mean, the angular position to move from one position to another position. So in this kind of case of application, we know that we would have rapid acceleration and deceleration to attain those position given. So instead of the motor continuously rotating with a speed that is defined, now the motor is going to rotate just to attain position instead of speed. So the speed is now less important. I mean, it is embedded inside the position, because in order to have position, you need to move using speed. In order to have speed, you need to have a certain acceleration. So you can see in general, the idea of the loop embedded in one another is that in internal you have torque or current loop, and then you have speed loop, and from the outside you have the larger one would be the position loop. So DC servo drives is when we talk about position control. So the motors in this case of application are usually very small. There are small motors, because rapid acceleration, rapid deceleration. So therefore, if it is a large motor, then the inertia would be very high. If the inertia would be very high, then the torque that needed to accelerate that inertia will be very high, therefore very high current as well. So usually this kind of DC servo drives, DC servo motor, are especially used for small motor and designed to withstand high current, for intermittent acceleration and deceleration. So you can imagine a robotic application, it moves one side to another side and then it goes back. So acceleration, deceleration intermittently. So the rotor is usually designed to have low inertia to make sure that we pull not too much current. Therefore, in this case, if the machine is properly designed to have a low inertia and the winding able to withstand high current, the current loop can be redundant if in terms of topological design it is already it is already good to have a proper level of current. The current loop can be redundant and could be made unnecessary. So for example, in this case over here, in this schematic control diagram, what happened is that we can see that there is two embedded loop. Inside we will have a velocity loop or speed loop, and on the outside we will have the angle or positional loop, and we don't have a current loop inside in the middle. So we have, of course, here symbolized by the amplifier is the driver amplifier, all the components we have seen just now. And how does it operate? So it operates by first, of course, by defining the angle or position of reference that we want to attain, we want to reach, and the reference is set by, of course, by reference voltage, and it will be later compared to a certain real measurement. It is compared to actual position, which is measured, for example, in this case, using a potentiometer. So you might have a position that is measured by a potentiometer, and the voltage output from the potentiometer will be compared to the angle of reference, to the voltage of reference. If there is a certain difference, if the error is not zero, then the machine will continue to give a certain input of error. Therefore, asking the velocity loop to continue to deliver current to the motor. Therefore, the motor will continuously rotate. When the motor, once the motor has reached the position, therefore the error will become zero, right? The comparison will become zero. Therefore, there will be no voltage supplied to the velocity loop, and the motor will therefore stop rotating. So the motor is now is in the position that is defined by the reference in the command. So any position so in general, in the control loop, we can say that any position error will generate a command voltage, thus rotating the machine back to the desired position. So for example, if once it arrives at its position, if you have a load torque that try to pull it away from the defined position, then the error will appear. So if you have error, then you will supply back voltage to the motor so that the motor get back to the position that is demanded by the angle of reference. So the speed loop may be used to limit speed. So here we have a speed loop, right? So in this speed loop, what happened is that, so angle position give an error in terms of voltage. So the voltage over here will be sent into the voltage loop. It will be compared with the real voltage. So of course, instrumentation of measurement is tacho generator or an encoder. The most important is that you have the information of the velocity. So it's compared with the error. If basically if there is still error, then the information will be basically converted into current that will be delivered to the motor. So in this drive amplifier, we could add a certain block, for example, the block of controller, where we can basically limit the speed. For example, if the speed is too high, we want the speed in order for it to attain from one position to another position not to be too fast. For example, it may be due to the limitation of mechanical strength, so that we don't have too much centrifugal force, for example. So the speed loop may be used to limit the speed to eliminate eventual overshoot. So for example, if there is too much speed, depending on the inertia of the machine, you might go beyond the position and it has to get back. You have overshoot and you have to go back to initial position, therefore accelerate in the opposite direction. So here is an example of the comparison. If you have a velocity loop, speed loop, or no speed loop, if you don't have any velocity loop, therefore the machine will just accelerate without any speed limitation. Therefore, it may induce to an overshoot. If you have overshoot, therefore it has to go back to the opposite speed, and if it is too much speed, then it will go into the negative overshoot. Therefore, you will observe a certain oscillation, which is not desirable, right? So without a feedback and the velocity loop, without the feedback of tachometer, you will observe an overshoot and oscillation response of the speed, like this, of the position. So it goes beyond the position that we want. So here is basically the position that we desire, go beyond, and then it has to go back and return again, so there will be an oscillation. So the type of controller that we may use, for example, we may use PID controller in the speed over here to make sure that there is no overshoot and we have the smallest error possible at the response. So that's about it. We have completed all the discussion on DC machine. So this week, to summarize, we have looked into two parts, the driver and the control part. The driver, we have looked at the two most basic type of power electronics to build the driver. The first one is the thyristor driver, thyristor fed machine. And then secondly, we have looked at the chopper or PWM driver. And then in control, we have looked at the usual feedback, speed and torque control embedded. And then we have looked just now at the addition of servo drive, which is basically a position control. So thank you very much. Until I'll see you next week for another topic. So now we have completed the topic on DC machine. We'll be looking next at induction machine. Before that, of course, there are several review questions that you may try to discuss with your classmate and try to look if you really understand the topic and if you are able to answer them. So there are more of a concept questions rather than calculations. Please discuss them, and you may ask me if there is any if there are any question raised. Okay, thank you very much, and see you in the next video lecture.